This is going to be part 1 of our comprehensive human anatomy review for the final coming up. Let's do this! Describe the human body in anatomical position. Anatomical position is when the body is standing up, palms are facing forward, and it is important because it provides a standard reference point for describing the human body. Describe how to use the terms right and left in anatomical reference. In anatomical position, right and left are going to be opposite of each other because in anatomical position, the person is facing you. So right and left will look opposite to what they are to you. Identify and describe the atomic planes in which a body might be viewed. The sagittal plane is when the body is divided into left and right halves. The transverse plane is when the body is divided into superior and inferior halves. And the frontal/coronal plane is when the body is divided into anterior/ventral and posterior/dorsal halves. List and define the major directional terms used in anatomy. Cue the YouTube short. Proximal and distal. Proximal means closer to the point of attachment of the limb. Distal means further away from the limb. For example, I would say that my elbow is proximal to my hand, as it is closer to the point of attachment, the shoulder. Or my index finger is distal to my shoulder, as it is further away from the point of attachment. Superior and inferior. Superior means above, and inferior means below. For example, the head is superior to the thoracic cavity, and the feet are inferior to the heart. Lateral and medial. Lateral means away from the midline, and medial means towards the midline. Posterior and anterior. Posterior means towards the back, while anterior means towards the front. Deep and superficial. Deep means further from the surface of the skin, while superficial means closer to the surface of the skin. Remember, you only use proximal and distal when you're talking about bony landmarks or anatomical regions on the same limb, whether that be arm or leg. Describe the location of body structures using appropriate directional terminology. This is the diagram you need to know for this LO. A good way to practice this is cover up each little region and then test yourself until you have memorized where each cavity is and be able to use the anatomical directions that we explained in the previous LO and be able to apply it to these cavities. For example, if you're asked the question, is the abdominal cavity inferior to the pleural cavity? You would say, yes, it is. Or if the superior mediastinum is superior to the pericardial cavity, yes, that would be true. Describe the location of structures of the body using basic regional and systemic terminology. This is the diagram that you'll want to know for this LO, and there's a Quizlet in the description to practice these terms. Describe, in order from simplest to most complex, the major levels of organization in the human organism, and give an example of each level of organization. Boom! Here's a perfect diagram right from the textbook that gives you the levels of organization and examples of each level to know. List the organ systems of the human body and their major components, and describe the major functions of each organ system. So you can find this in section 1.2 of the textbook, and essentially here is all of the organ systems and the major functions of each system. So this is mainly all that you need to know for this particular LO. Define homeostasis. Homeostasis is an organism's ability to maintain a stable internal environment despite external changes. So it's that set point. That's where the body always wants to be with everything. Define the following as they relate to homeostasis: set point, variable, receptor, effector, and control center. And list the steps in a response pathway. And list steps in a feedback loop. And explain the function of each step. The set point is the certain range where the body wants to be for homeostasis. For example, our blood pH set point is between 7.35 and 7.45. That is considered the homeostatic range for our blood pH. And another example is our internal body temperature. The homeostasis temperature for that is 98.6 degrees Fahrenheit. Anything above that, anything below that would be deviating from homeostasis. The variable is something that causes a change in homeostasis. So for example, let's say it's 0 degrees Fahrenheit outside, freezing cold. Our set point is 98.6 degrees for internal temperature, and the cold is the variable that is going to cause a change in our homeostasis temperature. The receptor is the sensor that picks up this change and sends that information to the central nervous system. So with our cold example, let's say, it's cold out, the cold is the variable. The receptor is going to be the thermoreceptors, because the thermoreceptors are going to pick up the change in temperature and send that information to the CNS. The control is what decides what we are going to do with the information that the receptors are sending to it. So with our cold example, the brain has to decide, what are we going to do with the information that the thermoreceptors are telling us about this cold temperature outside? The effector is what listens to what the control has to say. So in this example, it's going to be the skeletal muscle that listens to what the control is saying about cold temperatures, because the skeletal muscle is going to shake and you're going to shiver to generate heat to warm your body temperature up to get back to homeostasis. And that leads us to our response. The response is the action that your body is going to take to get you back to homeostasis in a negative feedback loop. So the response to the cold temperatures outside is skeletal muscles shaking and shivering to warm your body temperature up to get back to homeostasis. Compare and contrast positive and negative feedback in terms of the relationship between stimulus and response, and describe examples of each. A negative feedback loop is when you want to get back to homeostasis. A positive feedback loop is when you do not want to get back to homeostasis, right? So a negative feedback loop is to get you back to the set point, whereas in a positive feedback loop, homeostasis is not desired. Maintenance is not desired. So this is the example of the negative feedback loop that we were just talking through before, right? With the cold temperatures and how our response is going to be shivering to warm our bodies up. And in a negative feedback loop, see, we want to get the seesaw back to level, right? We want to get back to homeostasis. And we want to get rid of the variable in order to achieve homeostasis 98.6 degrees Fahrenheit again, right? Whereas in a positive feedback loop, we do not want to stay at homeostasis, right? So the biggest example of that is childbirth, right? With childbirth, we have our set point uterine contractions, which are usually little to none. They fluctuate with the menstrual cycle, but usually when you're not giving birth, there's not going to be many uterine contractions. Our variable is the baby that is ready to be born. The receptor would be the uterus and the cervix, which are going to contract to push the baby out. Our control is our brain, and the brain is going to release oxytocin to stimulate increased uterine contractions, right? So the effector is going to be the uterus and the cervix in this case, because that is what is being acted upon, and our response is an increased amount of uterine contractions to get greater and greater and greater to push the baby out, right? So with a positive feedback loop, we want to increase the impact of the variable as much as possible. We want the seesaw to be not level, because if it is level, how in the world are we going to get that baby out? So that's why we need to increase the impact of the variable, and we want to move further and further away from homeostasis in a positive feedback loop. Another example of a positive feedback loop is things like blood clotting and platelet aggregation, right? Like when we have a blood clot, we want to increase platelets in order to clot that blood. Well, we can't do that if we're just at a homeostatic level of no platelets being released to clot that area. Right? Or another example is lactation, right? When the baby suckles, we want more milk to be going to that area to where the baby can receive the nutrients. Well, we can't do that if we just stay at normal homeostatic level of milk production, right? It's the variable, the baby suckling, that increases the response, moving us further away from homeostasis, but ultimately gets us to achieve the desired outcome that we're looking for. Explain why a negative feedback is the most common mechanism used to maintain homeostasis. So a negative feedback loop is the most common mechanism because most of the time you want to stay in homeostasis, You don't want to be deviating from homeostasis. You want to stay there to survive. So that's why a negative feedback loop is used, because that is what gets you back to homeostasis. Some more examples of positive and negative feedback loops can also be found in Brightspace, right? So these are examples that Professor Fried posted and good examples to practice with. Describe a feed-forward anticipatory response, how it helps maintain homeostasis, and an example of a feed-forward response. So a feed-forward response anticipates an impending disturbance before that disturbance actually disrupts the set point, right? Because in a negative feedback loop, the goal of that is to get you back to homeostasis. But with an anticipatory / feed-forward response, the goal of that is to anticipate a change that is going to happen because of the activity that you're about to do. So for example, let's say you're about to go for a run. You know this, right? So your heart is going to increase as an anticipatory response to what is going to happen to your body, right? Because we know that our heart's going to increase when we run. So the body prepares for this, it anticipates this, and so it prepares for that to kind of get you ready for a change in homeostasis. Another example is when you're about to eat food. You know you're about to eat food, so you start to salivate, right? And this kickstarts the digestive process to prepare you for a deviation in homeostasis. Compare and contrast the terms atom, element, molecule, and compound. Got that terminology right here for you. Describe the charge, mass, and relative location of electrons, protons, and neutrons in an atom. All right, so protons, they're in the nucleus. They got a +1 charge, 1 AMU. Neutrons, in the nucleus, 0 charge, 1 AMU. Electrons are orbiting the nucleus all around it at the speed of light, -1 charge, and they got a 1 in 2,000 AMU. So some notes about charge, some notes about, just these general terms. The number of protons and electrons in a neutral atom is the same, and when they're the same, there's no net charge. So, for example, let's take a normal carbon. It's got 6 protons. There will be 6 electrons traditionally. And the charge is determined by the number of protons and electrons. And isotope is when there are different numbers of protons and neutrons because the atomic number is different. And the way that you calculate number of neutrons is you do atomic mass minus atomic number. So this is an isotope example. We have our normal carbon here with a mass number of 12 and an atomic number of 6. So mass number, atomic mass, they mean the same thing. This is our atomic number giving us 6 protons and 6 electrons. 12 minus 6, 6 neutrons. This is a carbon isotope. And it's an isotope because there's a different number of protons and neutrons because we have a different mass number. 13 minus 6 gives us 7 neutrons. Another thing to note is that an ion is when there are different numbers of protons and electrons. So let's say, for example, we have 7 electrons and 6 protons in a normal carbon. That is going to give us a charge of +1. So carbon it'll be C and then +1. Explain the mechanism of each type of chemical bond and provide biologically significant examples of each, covalent, ionic, and hydrogen bonds, and compare and contrast nonpolar covalent and polar covalent bonds. So a covalent bond is when you share a pair of electrons to achieve a full stable electron shell. So basically the goal of a covalent bond is you want to fill the outermost shell of electrons fully, which is the valence shell, right? So this is a great example of the equal sharing of electrons to achieve a full valence shell. We got 4 hydrogens here and 1 carbon. The atomic number of carbon is 6, right? Meaning that it has 6 protons and 6 electrons. So the first valence shell, 2 electrons fill it, and in the second valence shell, 8 electrons fill it, right? So with the number 6, we have 1, 2, and then 3, 4, 5, 6 6 filling the valence shell, but that's only 4 electrons. We need 8 electrons to fill it. Well, that's where hydrogen comes in. Hydrogen has 1 proton and 1 electron in it, and it's got a valence shell that needs 1 more electron to fill that valence shell. And it's only got 1 valence shell, meaning it needs 2 electrons to fill it. So when sharing 4 hydrogens with 1 carbon, it works out perfectly, because with the sharing, the second electron, the valence electron shell of carbon is now full with 8, and the 1 valence shell of hydrogen is full with 2. A nonpolar covalent bond is when electrons are shared equally between 2 atoms. So same example as above. This molecule is actually called methane. Methane is a great example of a nonpolar covalent bond because, as we explained earlier, all valence electron shells are filled. All right, and with a polar covalent bond, that's when electrons are shared unequally between atoms due to a very large difference in electronegativity. The biggest example of that is water. Now, most commonly, you will see nonpolar covalent bonds. Rarely will you see polar covalent bonds, but it's still good to know. And in terms of electronegativity, I'll link a good video that explains electronegativity on the periodic table very well, so we can add greater context into polar covalent bonds. So an ionic bond is when one atom transfers an electron to another. So in this example with sodium and with chlorine, you can see that sodium is located here on the periodic table. Chlorine is located here. So sodium needs, it's got to get rid of an electron, and chlorine basically has to gain 1 electron in order to stabilize both valence shells. And that's exactly what's going on here, is when instead of sharing electrons like we do with covalent bonds, with ionic bonds, we donate electrons in order to fulfill the valence shell of both atoms. List the following types of bonds in order by relative strength: nonpolar covalent, polar covalent, ionic, and hydrogen bonds. Compare and contrast the terms solution, solute, and solvent. A solute is the thing that is being dissolved. A solvent is the thing that is doing the dissolving. And the solution, when the solute and the solvent are uniformly distributed. Define the terms salt, pH, acid, base, and buffer. So salt is just NaCl. The definition of pH is it's the negative base 10 logarithm of the hydrogen ion concentration of the solution. So a pH of 7 is considered neutral. pH of greater than 7 is considered basic, and that means there's a low amount of hydrogen. But if it's less than 7, it's considered acidic, where there's a high amount of hydrogen present. An acid is a substance that releases hydrogen ions in solution. A base is a substance that releases hydroxyl ions in solution, and a buffer is a solution of a weak acid and its conjugate base. State the pH values for acidic, neutral, and alkaline basic solutions. Define the term organic molecule. An organic molecule is a molecule with a carbon backbone. Has to have carbon. Explain the relationship between monomers and polymers. A monomer is one individual small molecule, but a polymer is a bunch of monomers that are covalently bonded together, meaning they're sharing electrons. For the rest of the LOs, starting with define and provide examples of dehydration, synthesis, and hydrolysis reactions from the first exam, I'm going to link this document in the description, and this basically starts on page 11, and this just kind of goes into the rest of the LOs that were on the first exam. So you can take a look at that for a breakdown of each LO after this one, and you can also view the previous LOs, which are in wording above page 11 as well.